Welcome to the second part of phase plane analysis, the lecture that we started on the last turn. This is lecture 5.4 of Unit 5, Control Systems. So we talked about phase planes, and we drew the phase portrait for a simple mass spring damper system. Now today we're going to look at different methods of drawing the phase portraits. So phase portraits for nonlinear systems, right? So there are two broad categories. One is the analytical method, and the other is the method of isoclines, which is a purely graphical method, right? The analytical method is of two types. One is what we saw on the last turn. I'll show this with an example. One method is to get the solutions. So you have x1 dot is equal to f1 x1 comma x2, x2 dot is equal to f2 x1 comma x2. You solve this and you get x1 as an explicit function of time, right, as a function of time, and similarly get x2 as a function of time, and then eliminate time to get the relationship between x1 and x2. This we did on the last in the last lecture, wherein we got x1 is equal to x0 cos t, x2 is equal to minus x0 sin t, and then we eliminated these two to get x1 square plus x2 square is equal to x0 square. So this is one way of doing it analytically. The other way of doing it analytically is to straight away integrate and solve the equation directly. Now, how is that done? Say again, so this is the second way is eliminate time variable directly. How is that done? Because we have dx1 by dt is equal to f1 from this here. Similarly, we have dx2 by dt. To write in a compact way, it's f2. So I can write dx2 by dx1 as f2 by f1 and then integrate this directly. So in our case, we had this basic equation x double dot plus x equal to 0, and then we wrote the state variable form for this. We said x1 is x1 dot is equal to x2 and x2 dot is equal to minus x1. We get this from this. So when you put the first variable, you put the first variable as x1 is equal to x, you get x1 dot is equal to x dot, right? So sorry, your first variable is x1 equal to x, and the second variable x2 is x dot, right? So what are the equations that you get? The first equation that you get is x1 dot is equal to x2, here this one, and the second equation that you get x2 dot, you get that from this original equation. X2 dot is x double dot, which is equal to minus x is equal to minus x1. So this is how you get the state variable representation for this. So from the original differential equation, you get the state variable representation, and then you can write down your dx2 by dx1 as minus x1 by x2, and then you can integrate this. So you have x2 dx2 is equal to minus x1 dx1. For initial conditions, x1 0 is x0 and x2 0 is 0, right? So these are your initial conditions, because the the state is x0 and the velocity is 0 at time t is equal to 0. So when you integrate this from on both sides with respect to x2 here and with respect to x1 here, you'll get x2 square plus x1 square is equal to c, right? And then you can put in these initial conditions, so you get, and these are functions of time, so you get x2 square 0 plus x1 square at 0 is equal to x0 square, because x2 at 0 is 0 and x1 is x0, so is equal to c. So you get the final equation as x2 square plus x1 square is equal to x0 square, right? So this is another way of eliminating time and straight away getting the two state variables with respect to each other, getting their equation with respect to each other. Now the third method is called the method of isoclines, right? Method of isoclines. The second method, in fact, in which you're not basically solving it analytically. And how do we do this? Now again, we look at this this second order system that we have. X1 is dot is equal to f1 x1 comma x2, x2 dot is equal to f2 x1 comma x2, and we write this as dx2 by dx1 is going to be f2 by f1. And suppose we're trying to find out the points. Now this is the slope of the trajectory, right? Because what we're sketching on the phase plane is x2 on the y-axis and x1 on the x-axis. So dx2 by dx1 is actually the slope, right? And it represents the tangent to the phase portrait, the angle of the tangent to the phase portrait. So dx2 by dx1 is f2 by f1, and suppose we're trying to find the points, all the points where the slope is some constant alpha, right? So all the points where the slope is some constant alpha would be given by f2 is equal to alpha f1, right? Now this is how we use to sketch the phase portrait. We define an isocline as a locus of points with a given slope, right? Given slope. This is the mathematical definition of an isocline, and an isocline with a slope alpha is given by f2 is equal to alpha f1, right? And this basically gives us a field of directions of tangents to the trajectories. Field of directions of tangents to the phase trajectories, right? And from this field of directions we can draw the phase plane trajectories, right? How do you do this? Again, for this simple linear system is what I'm going to illustrate right now. It'll be easy to understand. So we just saw that the state space representation is this, right? And the slope dx2 by dx1 is minus x1 by x2. So let me write this down. So dx2 by dx1 is minus x1 by x2. This is the definition for the slope of the phase trajectory at any point x1 x2. And let me say that the slope is alpha, right? So the equation for the isocline becomes x1 plus alpha x2 equal to 0. So this is the equation for the isocline. Equation for isocline with slope alpha. What it means is that the locus of points with points on the phase trajectory with a given slope alpha is a straight line given by x1 plus alpha x2 equal to 0. Let me draw this now. Let us take the phase plane and say alpha is equal to 0. So all the points on the phase trajectory with a 0 slope. Now this is x2, this is x1, and alpha is equal to 0 means x1 is equal to 0. And x1 is equal to 0 is this line here. It's the x2 line. So this is the alpha is equal to 0 isocline. When I draw this line, what I'm basically drawing is the locus of all the points on the straight trajectory for different initial conditions with slope 0. Let me now take alpha is equal to say pi by 2, 90 degrees, right? Alpha is equal to 90 degrees, right? Which is equal to, in radians, if I want to write, I write alpha is equal to pi by 2. No, but sorry, we are talking about slope, so slope is tangent. So I'm for 90 degrees, I take alpha is equal to infinity. Tan infinity is tan 90 is going to be infinity. So let me take alpha is equal to infinity. So what is the locus of the points where alpha is equal to infinity? Alpha is equal to infinity means a slope of 90 degrees because tan 90 is infinity. So when alpha is infinity, you will get, from this equation, you will get the other line. You will get the line x2 is equal to 0. And this is very easy because you can always substitute alpha by beta, where beta is 1 by alpha, and then do some calculations, and you will get x2 plus beta x1 is equal to 0. And when you say beta is equal to 0, you get x2 is equal to 0. So this is the line where your alpha is 90 degrees, right? Alpha is infinity, and basically which actually means that the angle is 90 degrees. The angle at which it is cutting this isocline is 90 degrees. Let us take so this is the line x2 is equal to 0. Let us take another line, another slope, 45 degrees. 45 degrees, alpha is going to be 1 because tan 45 is 1. So 45 degrees, the line is going to be alpha is equal to 1. So it's going to be x1 plus x2 equal to 0. So x1 plus x2 is equal to 0 is x1 is equal to minus x2. This x1 is equal to minus x2 line we want to draw this x1 is equal to minus x2 line. So it's going to be like this, right? This one. This is alpha is equal to 1 line, where x1 is equal to minus x2. So this in this line, the slope is going to be 1, that is, it is going to be plus 45 degrees. Let us take, so this is, let me write down plus 45 here, let me write down 90 degrees here, right, and let me write down 0 degrees here, right, to see to write down the angles properly. And let us now take another value, and that value, say alpha is equal to -1, which corresponds to a slope of minus 45 degrees. So in this case, when alpha is -1, x1 minus x2 is going to be equal to 0. So x1 is going to be x2, this is the line. So x1 is equal to x2 line is this one, and here alpha would be -1. That means the angle, it corresponds to an angle of minus 45 degrees, and the line is x1 is equal to x2. So now what this actually means is that you have collected all the points here with slope 0. You have collected all the points here, right, with slope infinity. You have collected all the points here on which lie on the straight trajectory, and their slope is 1, right. The slope is 1 means that the tangent has an angle of 45 degrees, and you have collected all the points here whose slope is -1, which means that the tangent has an angle of minus 45 degrees. So if I want to now plot the field of directions, my phase trajectories should cut this at 0 slope. So they'll cut it like this, right, and they should cut this at 90 degrees slope. So they should cut this line like this, right, and they should cut this with a minus 45 degrees slope. So this is minus 45 degrees, right. So they should cut it like this, and they should cut this line with a plus 45 degrees slope. So they should cut this like this. It's plus 45 degrees. So this and other lines, if I want to draw them, gives me a field of directions, and I can see that if I join these lines, I should be able to get, circles. So without circles, right? So what I've done is basically constructed the phase portrait purely graphically for the system. I started by drawing the locus of points with a given slope. I drew those lines. They are lines in this case, it's simpler, but they may not necessarily be lines, they can be curves. Then I drew the directions by cutting the lines at the particular angles for which they had been drawn actually. And then I tried to see what is the shape that it actually gives me, right. So the shape that it gives in this case is easily seen to be a circle. So I can draw the phase portrait purely and purely graphically without actually solving for the system, and this technique is actually what is employed for nonlinear systems. We can extend this to some other linear systems with specific properties, and it's not very difficult because the next lecture will be primarily talking about nonlinear systems. So I'll conclude this here. So in case of linear systems, if you have a second order linear system, if you have poles like this, right, this is called a stable focus, right. We have just seen this phase portrait for a second order linear system which has poles like this, right, and a marginally stable system. Now suppose your poles are not like this, they're like this, right, then you'll get a phase portrait which is similar, but it is going to be stable, right. So it is going to spiral down, it is going to spiral, the displacements are going to be finally becoming 0. And in this case, If you have an unstable focus, right, if your focus is like this, unstable focus, these are linear systems, please remember, right? That's why we are able to draw the poles so easily. If you have an unstable focus, you'll have the same spiral, but it will be now, the directions would be outward, because these are increasing oscillations, right? The direction would be outwards, right? So it'll be something like start from the spiral, go out, right? This is an unstable focus. This is called the center point. Center point. And if you have a center point, it's a marginally stable system, you'll get a circle, right? So you get something like this. So these are three different phase portraits that we'll get for three different pole locations. There are other possibilities also. Suppose you have a typical pole location, stable, left hand side of the S plane, right? So this is the S plane. I hope you understand this, right? So if you have something like this, the first portrait would look something similar to what I'm drawing, right? It's going to be so the face portrait would be like this. So it's coming in from here, stabilize, coming in from infinity kind of, and going to 0. So this is called the stable mode. Stable mode. See, the phase portraits are converging to the equilibrium point, which is 0, 0 in this case. The equilibrium point is called the singular point in phase plane analysis. So you can have an unstable mode, which would be both the poles on the right hand side, no oscillations, because they have no negative they have no imaginary paths. So in this case, it's going to look like something again similar to what we have drawn, but slightly diverging instead of converging. So you draw these two lines here, and then we draw it inside like this. So it's diverging instead of converging. So it's going to be like this. So this is called the unstable mode. And you can also have for linear systems the saddle point. The saddle point would be when you have one pole on the left hand side, one pole on the right hand side. You're going to have something like this. In this case, the first phase portrait is going to look like you have diverging lines here, converging lines here, and then you have the portrait like this. This is called the saddle point. To summarize, we have drawn the phase portrait for a linear system, the system that we already saw. We have also seen that we can draw this phase portrait analytically, and there are two methods of doing it analytically. Graphically, we can do this by drawing isoclines, and we saw that we can get a circle for the system which was marginally stable. And if we do this for systems which have different kind of pole locations, we get typical phase portraits given by these formations here. Thank you very much for listening.